Okay, great. So thanks to Mark to agree to give us this talk, this lecture. So we have Marcus Spradlin from Brown, and he'll just introduce us to scattering amplitudes, or just amplitudes.
Yes. So I was asked to provide some references for this lecture, and of course, the canonical reference, as Yutin knows, is his book with Henriette Elvang. So I'll list this one first.
Yeah, and it's on the archive. Yeah, that's all.
Yes, it's on. It's available as a book, but it's on the archive under this archive number. So this is now a canonical reference. I certainly won't have time to go through everything, but if you want a comprehensive introduction to the field of amplitudes, you should start by studying this book and everything in it. There's also a very nice series of lectures written up by Clifford Chung. And at least the first portion of my lecture today is largely modeled after what he's done, although then I'll move on into some other topics. And also I have some TASI lectures from last year, which are available, the videos are available online. Okay, and my lectures today and tomorrow will be very similar to that. Okay, so let's start. The field of amplitudes is an enormous field in high energy theory research. And 6 years ago, there was an entire TASI summer school on amplitudes. And there's a huge gap between where graduate courses typically end, maybe studying some basic aspects of quantum field theory, and where you need to be in order to begin research in amplitudes. So my lectures are designed, I won't be able to fill that entire gap, but I'll at least be able to take you a few steps along the route to try to bridge that gap. So in order to make this as accessible as possible, let's start really, really basic. So let's start with things that many of you have probably already seen in your quantum field theory course. So let's talk about the definition of a particle. Because when we talk about amplitudes, we talk about the scattering of particles. So what is a particle? Okay, so this is due to Wigner, who pointed out that we should think of a particle as an irreducible representation, a unitary finite dimensional representation of the Poincaré group. And I remind you that the Poincaré group is in 4-dimensional space-time. It's the group generated by a 10-dimensional algebra consisting of 4 translations. So you have the translations in the space and time dimensions, and then you have 3 rotation generators and 3 boosts. So it's a group generated by 10-dimensional algebra. So he said when we talk about scattering particles, the things that we see as initial states or final states in our hypothetical scattering experiment should be unitary finite dimensional representations of the Poincaré group. Now, taking this definition has several advantages. One is that this definition doesn't care. There's no notion in this definition of whether a particle is elementary or not. And that's important because in quantum field theory, we've learned that the notion of whether or not a certain particle is elementary or not elementary usually doesn't have an invariant notion, because there are dualities that relate different quantum field theories to each other and it can happen, it typically happens in these dualities, that something which is an elementary particle in one duality frame or in one point of view is not an elementary particle from a different point of view. Yet if you have a duality, it should map the entire set of scattering amplitudes from one theory to the other theory. So this definition Wigner proposed has one advantage, that we don't care about whether particles are elementary or not. Okay, so I'll just write don't care if elementary or not. Another nice advantage of this is if you've had quantum field theory recently enough that you still remember it well, if you remember the derivation of the LSZ reduction formula for how to calculate scattering amplitudes from amputated Feynman diagrams, you remember that in a generic quantum field theory, there are many different operators that create the same asymptotic states. Okay, so this eliminates the need, to worry about the infinite redundancy that many operators create the same asymptotic states. Now this is unlike in a CFT. So in a conformal field theory, if you've studied CFT, you know that the operator state correspondence tells you that there's a one-to-one correspondence between local operators and states in the theory. Now, when we talk about scattering in a generic non-conformal field theory, there's an infinite redundancy because there are infinitely many different operators that create the same asymptotic states. I referenced earlier the derivation of the LSZ formula, and if you remember back there, there are only a few conditions you need to impose on your operators. For a particle of mass m, you want an operator whose two-point function has a pole with residue 1 at m squared. There are just a very few conditions on the operator for it to create an asymptotic state of the type you might be interested in. So Wigner's definition of a particle as a unitary finite dimensional representation of the Poincare group means we don't have to worry at all about what operator might be creating that particle. But anyway, I'm dwelling too long on this point. Okay, so let's talk about these irreducible representations. Let's consider a momentum 4 vector. Okay, and under orbits of the, let's consider the proper ortho-chronous that means Lorentz transformations that preserve parity and that do not reverse the direction of time. I should say that there's 6 different kinds. Well, I should have said there's 6 different orbits. Okay, let me. Okay. Okay, so let's just write them all one at a time. Of course, if you have the 4 vector that's identically 0, you do any Lorentz transformation, this will come back to itself. So this is a single point under the action of the Lorentz group. You can also have p squared greater than 0, and here I need to specify, let me work in signature -1, 1, 1, 1. Okay, so in this signature, any particle with p squared greater than 0 is a tachyon, which we usually consider to be unphysical, so I won't discuss this further. We could also have p squared equals 0. That would be a massless particle. And then there are 2 separate cases to consider. We could have the energy component or the time component either being positive or either being negative. So these two types of four momenta, you can't reach from one to the other under a proper ortho-chronous Lorentz transformation. Okay, so these two would correspond to massless particles. The first type having positive energy and the second type having negative energy. Okay. Then, of course, we can finally have p squared less than 0. These would correspond to massive particles. And again, these split into two groups or two sets. Okay, so to review what we've done here, you give me an arbitrary four momentum, and it falls into one of these 6 classes. And within any one of these 6 classes, you can get from any p mu to any other p mu within the same orbit by the action of some element of the Lorentz group. Okay, so Wigner said the following. Okay, so obviously the ones that are going to be of interest, let me try my highlighter function here. We're going to be interested in the positive energy massless particles and the positive energy massive particles. Now, it is true, of course, that when you use quantum field theory, you often talk about, when you talk about incoming or outcoming fields, you allow yourself to analytically continue the energy from positive to negative, and that's a useful trick. But for the purpose of classifying actual particle states, it's sufficient just to focus on these positive energy guys. Okay, so let's start. Let me do, okay. Any massless or massive, I'll do these two in parallel for momentum p mu, can be brought into a standard form. Okay, so I hope my notation here is clear. Oops, 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 oops. That was the eraser, not the highlighter. Sorry. Okay. Okay, so the point here is if you have a four momentum corresponding to a massive particle, you can always go to the rest frame of the particle, and then it will take this form down here in the lower right. So you can, by Lorentz transformation, you can put it in the rest frame, so it will have a non-zero component only in the first component of the 4 vector, the time component or the energy component. On the other hand, if you have a massless particle, you can always do a Lorentz transformation so that it's, it has to move at the speed of light, but you can do a rotation so that it's pointing along the z-axis. So that's what I've done here. So we call these the standard forms or reference momenta. So if you give me any one of these types of 4 momentums, I can do a Lorentz transformation to bring it into this form. So to finish the sentence, can be brought into standard form by a suitable Lorentz transformation. Okay. By the way, if there are any questions, don't hesitate to shout them out. So what we're going to do is, suppose we have a basis of states for all of, well, let me write it here. A basis for all states with a given k mu. And these sigmas, oops, some labels. Okay, so, and now whenever I use k mu, you should understand that I mean it to be one of these reference momenta. And whenever I use p mu, you should understand that I mean it to be completely general. Okay, so suppose we have some collection of states for a given reference momentum k mu. I don't yet know how many states there might be. We say 1,025. And we're going to let sigma be whatever labels you need to distinguish those 1,025 states. Okay, then to proceed, for any p mu, choose a Lorentz transformation L mu nu. Remember, Lorentz transformation is a 4x4 matrix. This will depend on p and k such that p mu equals L mu nu p k k nu. Okay, so earlier we said that any p mu can be brought into the form of a reference for momentum k mu by a suitable Lorentz transformation. So here we're going to let capital L be such a Lorentz transformation. Now, obviously, and this will play an important role in just a moment, for given p and k, L is not unique. Right. For example, let's say you have a massive particle. Once you've brought it to the rest frame, you can additionally do any arbitrary spatial rotation, and it will still be in the rest frame. Or for a massless particle, once you've aligned its momentum along the z-axis, you can still do any rotation around the z-axis without changing it. Okay, so then we assume, and this is here comes Wigner again. We assume we have a unitary finite dimensional representation, oops, of the Lorentz group acting on our Hilbert space. So the word representation, I remind you, just says that for every Lorentz transformation L, we have some unitary operator U. So we have U of L. Okay, so we have all the ingredients now. Let's do a very short derivation. Here we assumed we have some basis of states for the reference momenta. Now we're going to use our assumed representation of the Lorentz group to define a set of states for arbitrary momenta. So let me add color to add a little bit of spice here. So we define just by the obvious thing. Sigma just goes along for the ride. This is whatever other collection of indices we need to specify the states. And we're saying that here we have a Lorentz transformation L that takes us from K to P. So to define the state P, we just take that Lorentz transformation, take the unitary operator associated to it, and act on the state K. Okay, seems like a totally reasonable definition. Now, consider what happens. How does the state P transform under a further Lorentz transformation? Oops, that was a mistake. So here's how we're just going to do a quick calculation. Consider U of L prime. Okay, so we're going to do we're going to take this state that we've defined and do some other Lorentz transformation on it. Now, because we have a representation of the Lorentz group, so just to
So,
remind you, oh, is there a question?
Yeah. So what about
Oh,
translations?
I'm sorry? Oh,
What?
excellent. Yes, I haven't yet discussed translations. That's coming. Does it? Yeah.
Okay.
Yeah. Yeah. Good. Good. Here I've only been discussing the Lorentz group. Yeah. Any other questions? Okay. Now, because we have a representation, remember that representations satisfy u of a times u of b equals u of a times b. So using that formula, I can continue my derivation from above and write this as u of L prime L p k, k of sigma. Okay. And now here's what I'm going to do. I'm going to insert the identity in a clever way. This equation is going to get a little bit difficult to unpack. Yeah, let me give myself some more room here. Okay, what I'm going to do is insert a factor of the identity. And then I'm going to take this and save myself some room by not writing it again. Okay, so what have I got here? I've got Lorentz transformations form a group, so everyone has an inverse. So here I've inserted an inverse transformation and the corresponding transformation. I don't quite have a pointer. Well, inside the argument of here you see this thing, oops, and there's an extra comma that shouldn't be there. Sorry, let me try to rewrite this. Okay, so in here, you've got the Lorentz transformation L prime applied to P. Okay, then this thing is L times L inverse, so that's 1, and then the box is repeated from what I've got below. Okay, so to continue this derivation on the next slide, on the next line, this is u of L prime p k. And then I'm going to define w. Now let's not lose track where w is equal to L inverse L prime p k L prime L of p k. Yeah. You see, I just, I moved this down here. And then I split up these two factors. This one I pulled here, and this factor I pulled down here into my W. Okay, now here's really the crucial point. Notice that W is a Lorentz transformation that does not change K. In other words, W acting on K, if you want to be precise and I've suppressed the Lorentz indices in order to keep my sanity here. But if you wanted to restore the Lorentz indices on your Lorentz transformations, W mu nu, K nu is equal to K nu. Now, why is that? Let's take a look and just take a look at the formula and see why that's the case. So look back here at my formula for W and imagine that you take this thing and you hit it, you act with it on K. Well, the first thing that's going to happen is this is going to act on K, and by definition, that's going to Lorentz transform K into P. Then we're going to do this Lorentz transformation that transforms P into L prime acting on P. Then here we've got this Lorentz transformation, but it's the inverse. So instead of being the one that takes K to L prime acting on P, this is the one that takes L prime acting on P back to K. So you see, if you read this equation from right to left, this Lorentz transformation W has the property that it takes K, takes it to P, takes it to L prime P, and then takes it back to K. That completes the proof that this Lorentz transformation doesn't alter K. Okay, so therefore, U of W acting on K sigma must be a linear combination of other states with the same K. So to write the final, because W preserves K, and we've assumed we have a finite dimensional space of states with a given K. So when you act with this unitary operator U of W on K, it has to keep you within that finite dimensional space. And so the final formula for this, I'm running a little bit slower than I intended to, but I think I'm having fun. So the final formula was this one. Okay, and now here I'm going to replace this with and I've introduced some new notation here, sum coefficients. Oh, there's a typo here. This shouldn't be a double sum. I'm not summing over sigma here. Okay, a few moments ago, I said that this state should be a linear combination of states within the basis that I've already defined. So that's what I've written here. I've written some general linear combination of states of this type with coefficients that might depend on W and might depend on sigma. So this equation makes perfect sense. When we do a Lorentz transformation on the state P sigma that we've defined, we get exactly the expected operator sitting out in front here. We get the unitary operator associated to the Lorentz transformation that takes you from K to L prime P, but we might have a non-trivial mixing up of the states within our finite dimensional space. Okay, so the conclusion from this little exercise is that our one particle states lie in representations of the so-called little group. Oops. And the little group is defined as the set of Lorentz transformations that preserve K. Okay, so to be specific, for a massive particle, oh, by the way, I should have said this, but just to keep things sane and easy, I will always be restricting in these lectures to 4 space-time dimensions. There's a lot of interesting things one can say about amplitudes in different dimensions. Some of the things I'm going to say translate trivially. You can define the little group in any number of dimensions. Some of the things I'll get to in a few moments, you can only transcribe to other dimensions with more effort. But just to keep these lectures as clear as I can, I will be restricting to 4 dimensions. So for massive particle, the little group is SO3. That's in 4 space-time dimensions. And I already said that. That's because you can do an arbitrary spatial rotation, and that will preserve a particle in its rest frame. And for a massless particle, the U1 comes from rotations around the z-axis, and this corresponds to the E2 is the 2-dimensional Euclidean group. Okay. That is because you can do a translation in the plane perpendicular to the 4 momentum spanned by that your massless particle has. Now, there is some potentially interesting physics here, but we're going to ignore this for the moment because this is a non-compact group, and so it doesn't have finite dimensional unitary representations. Oops. Okay. So to be more specific, for a massless particle, if you do a Lorentz transformation that's given by a rotation by theta around the z-axis, acting on this state k mu, that should bring you back to e to the IH theta k mu, where the eigenvalue I'm just looking for here for finite dimensional unitary representations of U1 or SO2. Okay, and those are realized in this way. The eigenvalue H is called the helicity. And for topological reasons that I'll just brush aside in these lectures, it's quantized to be a half integer. Okay, whereas for massive particles, as I've already said, maybe I don't even need to repeat it, but states have to lie in representations of SO3. That is the little group for massive particles. Okay, so the conclusion of this section is that by consideration of the Lorentz subgroup of the Poincaré group, we found that we should think about massive particles as being labeled by, if you will, not only their mass, of course, but also by some specific representation of SO3, and massless particles should be represented by, or should be labeled by, is a better word, a helicity, which is half integer. So this is actually something you're already somewhat familiar with. If you think about a photon, which is a massless particle of spin 1, it has 2 possible polarization states. It can have, say, right-handed or left-handed polarization corresponding to helicity 1 or -1. If you have a graviton, a massless graviton, it can have two polarization states, +2 or -2. Okay, now we want to introduce a notation that will help us keep manifest track of this bookkeeping. Okay, so when you introduce a Lagrangian to describe, oh, is there a question?
Yeah, there's a question in the chat. So before,
okay. Yes, yes. So yeah, I was going to make a comment somewhat related to that. Is the one particle Hilbert space we construct using creation operators, like for a scalar field, an example of the particle Hilbert space we defined here. Yeah, so when we talk about, that's right, when we talk about a one particle state in quantum field theory, that's exactly what we have in mind here. Yeah, I'm not doing anything different. Are we considering massless fermions? That's why there's a second question. Are we considering massless fermions? That's why the helicity is half integer. Well, for fermions, we could consider massive or yeah, so you could have massive or massless fermions. And there's an accident here that if you consider a massless fermion, then you use this part of the table and you say, okay, the helicity can be 1/2 or -1/2. If you have a massive fermion, okay, if you have a massive fermion, you go to this part of the table and you want to have a representation of SO3. Now, I should have been more precise here, because as you know, fermions lie in representations. Okay, so let me just write here, SU2 is what I should have said. You know that SU2 is a double cover of SO3, and fermions live in representations of SU2 that are not honest representations of SO3. They're projective representations. But anyway, so yeah, what I'm trying to say is that fermions are kind of an interesting case where this and this happen to look pretty much the same as far as the kind of states that you get. Okay, are there other questions? Okay, so we want to now introduce a notation that will allow us to construct amplitudes for these scattering particles that make manifest the Lorentz transformation properties that we've discussed. So let's do the two cases one by one. If we have a massless particle, its momentum is 0. Now it's useful to think about the momentum as a 2x2 matrix by contracting with the Pauli matrices. And if you write it out in terms of components using the traditional conventional definition of the Pauli matrices, you get something like this. Okay, then the condition that p squared is equal to 0 is the same as the condition that the determinant of this matrix is 0. Okay, so from now on, I'll frequently find myself omitting indices. Hopefully, it should always be clear by context whether I'm talking about P as a 4-vector or P as a 2x2 matrix. You can always go back and forth between them. So here, when I say P squared equals 0, obviously I'm talking about it as a 4x4 matrix. I'm sorry, 4-component vector in Minkowski spacetime. And here, when I say determinant of P is 0, I mean thinking about it as a 2x2 matrix. Now, when you have a 2x2 matrix with determinant 0, that means the rank of the matrix is at most 1. So this implies that it is possible to express P as an outer product of two-component objects. The two-component objects, lambda and lambda tilde, are called spinor helicity variables. If you want to see it written out explicitly, so you have to be a little bit careful here because this thing here is not an, the thing that looks like an I subscript is actually a 1 dot, okay, not an I, not a lowercase I. So this automatically satisfies, you can check p squared equals 0. There's a question in the chat, can the spinor helicity formalism be generalized to higher dimensions as well? Partially, yes. For example, there's a 6-dimensional analog that, so for this I will refer you, Yuten, do you discuss this in your book or only in your papers? Okay.
It's in the book, yeah.
There's a section in it on the book? Okay, yeah. Please refer to Yuten's book for this one. In some sense, it's nicest in 4 dimensions, but there certainly are very useful features of it that can be applied to certain other dimensions as well. Okay, now, given P, obviously, lambda and lambda tilde are not unique. For example, if you do a transformation, and this particular choice is not an accident, you'll see in a minute. If you do some complex rescaling like this, this leaves P unchanged. Okay, so going back to our formula, P is defined as the product of lambda, lambda tilde. So if I just do an overall rescaling of lambda by this factor and an overall rescaling of lambda tilde by the corresponding factor, that leaves P unchanged. Now, why have I chosen these to be complex conjugates of each other? And that's just, if you want the momentum vector to be real in 3+1 dimensions, you should choose lambda tilde to be the complex conjugate of lambda. That's why in this rescaling here, I've chosen them to scale with complex conjugate factors. However, as you're probably familiar, it's often useful to forget about the requirement that P mu should be real. So it's often useful to consider scattering amplitudes when you've allowed yourself to analytically continue to arbitrary values, arbitrary complex values of the kinematic variables. This is useful when you're talking about loop level scattering amplitudes. This is useful because those amplitudes have complicated analytic structure, and you can gain a lot of information by looking, let's say, at discontinuities or poles of scattering amplitudes. And when you're talking about tree-level scattering amplitudes, those are always rational functions of the kinematic variables. So it really doesn't matter, you know, if you've got a rational function, it doesn't matter whether you restrict your attention to real variables or allow them to be complex. It's the same expression. So it's often useful to allow lambda and lambda tilde to be arbitrary. Not necessarily complex conjugates of each other. Okay, so we can do the following. Right. Okay. Yeah. Okay, there's another reason why I wrote this formula, and I didn't mention it. If you work out, you know that the Lorentz group, which has the algebra of SO3, 1, the algebra is isomorphic to that of SU2 cross SU2 at the level of Lie algebras. So as you might be familiar, this decomposition where you replace the single 4-component index mu by this pair of indices alpha and alpha dot is a way to manifest that. So the alpha index here is the one that transforms under SU2 left, and the alpha dot is the one that transforms under SU2 right. The reason I'm bringing that up is, remember we said that if you have a massless particle and you've chosen its momentum to lie along the z-axis, then you can do an arbitrary rotation around the z-axis, and that constitutes an element of the little group. Now, if you work out how such a transformation acts at the level of SU2 cross SU2, you will discover that it acts in precisely this way on the spinor helicity variables. Okay, assuming for the moment that I'm talking about a moment, so more generally, so let me write a formula here. Okay, if you do a rotation by angle, I should have clarified this earlier. If you do a rotation by angle theta around the spatial three-vector P of a massless particle, you can check that its spinor helicity variables transform as above. Let me just denote, rather than rewriting that equation, I'll reference it above. Okay. That's why I chose to use that. That's why I chose to call this theta, and that's why I chose to put that 1/2 there, because that's just what you get. All right. Okay. So now comparing to our previous formula, where was it? Way up here somewhere. Yeah, this one. Okay. Remember that a particle of helicity h transforms with a phase factor of e to the I h theta as you do such a rotation. So this brings me to the following statement. Okay. This is how the one particle states of a massless particle should transform when you do that kind of rotation, a rotation of angle by angle theta around the direction in which, the spatial direction in which the particle is transforming. Okay. Or if we complexify, and that means allow lambda tilde to be arbitrary, not necessarily complex conjugates, then we can write a more general formula that looks like this. I'm going to change the sign. It's conventional to change the sign. Okay, and then just let me write one sentence. Note that the two states here have the same value Okay, remember that P, the momentum, was defined as the product of lambda tilde. So if you multiply lambda by 1 over t, and you multiply lambda by t, then the t and the 1 over t will cancel out. So both of these two states have the same value of momentum. So here, the reason for writing this formula is this tells us how a one particle state should scale under a little group transformation. So we've learned, well, this is really a transformation of the complexified little group, because at this stage we can actually allow t to be an arbitrary complex number. Well, it shouldn't be 0, but other than that, it can be arbitrary. We don't require that it be on the unit circle. If you wanted to restrict to real momenta in Minkowski spacetime, then it would have to lie in the unit circle. So this formula tells us how a massless one particle state should scale under a, I'll write here, complexified little group transformation. Okay, now why have I done this? Okay, it may not be clear where I'm going, but the point is that just this knowledge places enormous constraints on formulas for scattering amplitudes because of the following fundamental assumption. This is really the fundamental assumption of the S-matrix theory. Why have I spent like over 40 minutes talking about properties of one particle states if they weren't going to be relevant for S-matrix theory? The fundamental assumption of S-matrix theory is that the S-matrix transforms, I'm sorry, let me write it a different way. The Poincare group, of which so far I've discussed almost only the Lorentz part, the Poincare group acts on the S-matrix as it does on individual one particle states. Okay, that's a beautiful sentence. Let's transform that sentence into an equation that we can use. So if we have an amplitude for n particles, Okay. For the moment in this discussion, well, I guess, yeah, and at the moment I'm discussing massless, okay? We'll throw massive into the mix in just a second, but the spinor helicity, the way I've defined it at the moment, is only for massless particles. We'll upgrade it in just a second. If you have an amplitude for n massless particles, then it should scale. Oh, sorry. Let me add a sentence here. Having helicities h1, h2, up to hn, those are all half integers, then A should scale oops. Hold on, let me write the formula. Oops, too many dots. Okay, so before I write the right-hand side of the formula, here's the important point. This now definitely is an I, not a one dot. Okay, so we're gonna do a little group transformation only on one of the particles, right? So the whole philosophy behind scattering here is that asymptotically in the far future or in the far past, these individual constituents of the scattering process behave as one particle states, and you can ignore everything else. So these are going to be unchanged. Let me call this original amplitude just capital A. Okay. So now I'm going to ask what happens if I do a little group transformation just on a chosen particle I. So that means I'm going to rescale the lambda variables for particle I by 1 over t, and I'm going to scale the lambda tilde variables for particle I by a factor of t. The right-hand side of this equation should be the scaling factor t to the 2hi times the original amplitude A. So in other words, the amplitude should scale separately, consistently with the one particle stage for each of the n particles. Okay. Are there any questions about this formula? Because we're going to get a shocking amount of information just from this formula. Yes. So there's a question here. How does the two-dimensional Euclidean group, which I quickly brushed under the rug, how does it act on the spinor helicity variables? Yeah. I feel like this is an embarrassingly simple question, but the answer isn't at the top of my tongue, because we usually ignore the. Yeah, let me just pass on that question. Good question though. Yeah, there is some interesting physics there, and yeah, but I'm not prepared to say anything in a recorded session. Any other questions? Okay, good. All right, so here we're going to see that 3 particle amplitudes and for the moment I'll stick with massless, sorry. Okay, so let's say we have three particles having momenta P1, P2, and P3. Okay. So far, in fact, one person asked about this already. I've almost only discussed the constraints from the Lorentz group, the Lorentz subgroup of the Poincaré group. But you know very well what are some constraints from the Poincaré subgroup, and that is that the overall momentum and energy should be conserved due to translation invariance in space and time. So we have P1 plus P2 plus P3 Oh, and by the way, it's conventional now. I may have made a glancing reference to this earlier. It's conventional when you're talking about an n particle scattering event and you have a certain number of particles incoming and a certain number of particles outcoming. It's conventional to imagine analytically continuing that scattering amplitude so that, let's say, all of the particles have outgoing momenta. Okay, then well, what that means is that some of them will have a positive time component and some of them will have a negative time component. But we do that because it makes the bookkeeping somewhat easier, because we can allow ourselves to write a formula like this: P1 plus P2 plus P3 equals 0. If we didn't do that bookkeeping trick, we would have to put a minus sign here relative between the incoming and outcoming particles. But it's really convenient to imagine that all the particles are outcoming, but some of them might have negative energy, and those we secretly in the back of our mind understand as having been the ones that were originally meant to be incoming. Okay, so because of these two constraints and because they're massless, because of these constraints, because of this momentum constraint and the massless condition, as you know very well, we have P1 plus P2 squared equals P1 plus P3 squared equals P2 plus P3 squared. Okay, now I'm going to introduce a little bit of notation. If you rewrite these equations, so these equations I've implicitly imagined writing in the 4-vector notation. But if you go to the 2x2 matrix notation, then P1 plus P2 squared turns into the following expression. It turns into basically 2 times epsilon. There may be a sign here depending on conventions. Running out of room here. Oops, yeah, I ran out of room. Let me try this better. So what I'm going to do is I want to rewrite this in terms of the spinor helicity variables corresponding to particles 1 and 2. Okay, so that's just an identity you can check. And now I'm going to make a definition. That I'm going to define. Let me switch colors here. I'm going to define the Lorentz invariant inner products for the SU2 left and SU2 right. Okay, so there will be 2 kinds of inner products with square brackets and curly brackets. Like this. There's a question in the chat that I'll be able to answer better in just a second. Okay, so so the interesting thing is that these quantities here, when I use the spinor helicity notation, they factor. Notice that this piece completely factors from that piece. So the upshot is that in three particle massless kinematics, we have the following equation. We have 1, 2. Often I will omit the comma here when it's clear. Okay, there's secretly a comma there, but I'll probably omit it just for laziness. Okay, so here I have these three. I'm referring to these three equations, that these three things should all square to 0. And when I write them in spinor helicity notation, I get these three equations. Now, if we were forcing ourselves to work with real momenta, then the as I said before, the lambda tilde variables would be the complex conjugates of the lambda variables. So, for example, this 1, 2 would be the complex conjugate of 1, 2. And so the first equation here would tell me that they both have to be identically 0. But if you allow yourselves to imagine considering complex momenta, then you can have two branches of solutions. You can have either, so I'll just write, with complex momenta, there are two non-trivial branches of solutions. You can either have notice, I didn't mention this, of course, but notice that these brackets are antisymmetric. So, so 1, 3 is negative 3, 1. So if one of them is 0, the other one is 0. So don't be alarmed by the fact that I changed the order there. You might be slightly curious why you can't have a more interesting scenario where, say, why don't you have 2 of the square brackets vanishing and 1 of the curly bracket or angle brackets vanishing? That doesn't happen because remember that all of these spinor helicity variables are 2 component objects. So if you look at something like this, if you say that 2, 3 equals 0, well, let me just write it like this. So note that if 1, 2 equals 0, this implies that lambda 1 is actually proportional to lambda 2. Okay, you're saying that you've got two. Think about it. You have two component vectors, and you're saying the determinant of the 2 by 2 matrix that you get when putting them together vanishes. That means they're proportional to each other. So if 1, 2 is 0, and let's say 1, 3 is 0, then lambda 1, lambda 2, lambda 3 are all proportional. So 2, 3 is 0 automatically. So as soon as any 2 out of these 3 conditions is satisfied, the third one is automatically satisfied. And the same goes here. That's why these are the only 2 sort of interesting scenarios. You can't have 2 of one type being 0 and 1 of the other type. Okay, so there are two types of massless three-particle amplitudes. In 4 dimensions, of course. You can have an amplitude that's a function of 1, 2, 2, 3, and 1, 3, or an amplitude that's a function of 1, 2, 2, 3, 3, 1. Now magic is just going to come out of thin air. Okay. I'll call it magic. There is a unique. Now, the next step should remind many of you, if you've studied conformal field theory, you know that there's an essentially unique, that means unique up to an overall constant. There's a unique formula for the 3-point function of conformal fields of given scaling dimensions. And essentially the same, we're going to see an essentially identical kind of formula pop up on the next line as a consequence of rescaling the scaling properties that the amplitude has to satisfy under little group transformations for massless particles. So there's a unique formula A equals I'll need to continue on the next line. That satisfies, and let me be clear, there's an overall constant here that's undetermined. That satisfies the necessary scaling. Now, in the case of conformal field theory, you may be familiar with the fact that, I'm just making an analog here because some of you might be familiar. When you have higher point functions, you have a piece of the correlator that's determined by the scaling, and then you could, in principle, have an arbitrary function of cross ratios. Here, the analog of that statement for amplitudes is you have a piece of the amplitude, some overall factor that's dictated by the requirement that it transform correctly under little group scaling. And then you could, in principle, have an arbitrary function of Mandelstam invariance. That means things that are genuinely invariant under Lorentz transformations, rather than things like the amplitude, which has to scale under the little group. But here, for 3-particle amplitudes, there are no Mandelstam invariants, right? P1 squared, P2 squared, P3 squared, they're all 0. So there is no possible functional dependence that you could have on anything else. The only possible ambiguity, which we haven't determined, is this overall undetermined constant, which I've called alpha here. Okay. So, right. Okay. Now, again, here we've derived these amplitudes, imagining that we've allowed ourselves to analytically continue away from real momenta in Minkowski space. But if we want to have scattering amplitudes that at least have a chance to define the real world, they better have the property that as we imagine analytically continuing back into the, let's call it the real momentum slice in Minkowski space, as you analytically continue back, you should have an amplitude that's well defined. You don't want to hit a singularity exactly on the Minkowski space locus. So in order to avoid a singularity on the Minkowski space locus, and I remind you, that's where all of these are equal to 0. Oops. We require that h1 plus h2 plus h3 is less than or equal to 0. Now, where does that come from? Well, there's a little bit of delicacy here, but you want to imagine taking a limit where all 3 of the variables appearing in this equation go to 0. So you might worry, okay, maybe it depends on the direction of approach, but okay, but anyway, you want to make sure that this thing at least doesn't blow up as you go to the Minkowski space locus. And so that implies the constraint that the sum of all of these helicities should be negative. Otherwise, alpha is equals 0 is the only solution with a smooth Minkowski space limit. So the only possible scenarios where you can have sensible 3-particle amplitudes are for collections of helicities satisfying this constraint. So let's look at some explicit examples. Oh, right. Okay, and there's a question in the chat that I'm going to get to in just a second. Well, I can say it now. Yeah. So the question is whether this is true to all loop order or it holds at tree level only. So nothing that I've said so far has made any reference to loop order or even to perturbation theory. So this, in fact, is a completely non-perturbative result. Okay. So the 3-point amplitude is completely determined just by these considerations. Okay. So in that case,
Mark, I had a question.
Oh yes, there's another question. Please.
The constraint that h1 plus h2 plus h3 should be less than or equal to 0. How do you get that?
Yeah. So if you just imagine. Okay, let's thank you because I just fudged that. Imagine setting. I think the way to do it is 1, 2 equals 2, 3 equals 1, 3 equals epsilon, and then you want to take the epsilon to 0 limit. Well, referring back to this formula here, A would be epsilon to the power. Let's add up the powers here. You see, each h comes twice with a negative sign and once with a positive sign. So we're going to get minus h1, minus h2, minus h3. So to have epsilon goes to 0 limit makes sense. We should have h1 plus h2 plus h3 less than or equal to 0. Thank you for asking that question. Is that clear?
Thank you, yes.
Yeah. Again, I mumbled something earlier that you might wonder, well, what if I take a fancier limit where I'm scaling? Okay, I don't know. But this is a naive argument that we usually make to justify that point. Okay, so let's look at some actual 3-particle amplitudes. Let's consider spin 1. So that means helicity can be +1 or -1. Yeah, by the way, usually when people learn quantum field theory for the first time, you learn scalar field theory because it's the simplest, it has the simplest Lagrangians to manipulate, the Feynman rules are the simplest, etc. But when you study amplitudes from a ground up approach, like we're doing here, actually scalar particles sometimes they're a little bit more subtle. I mean, here, you know, with a scalar particle always has helicity 0. So these amplitudes are just constants, and they're a little bit less nice. So that's why, oops. That's why here, when I'm going to this example, you see that I'm starting not with spin 0, but with spin 1. And so the reason is it's a better showcase for what we actually do in amplitudes a lot of the time. Okay, so we need, there are only a finite number of choices. We need to pick 3 helicities. Each one should be +1 or -1, and their sum has to be negative, according to this criterion that we've just discussed. So, for the moment, let's not care about possibly exchanging the different particles. So it turns out there are only 4 different choices that are allowed. We could imagine all the particles having negative helicity, and then just plugging into the formula. Oh, so the notation here is that I'm going to use these little superscripts to denote the helicity. Okay, so that's going to be the convention that I use. So I'm just going to put a minus sign when I mean that particle 1 has helicity -1. Okay. Now, referring back to this formula, if all of these are negative, if all of these helicities are -1, then my amplitude is just the product of all these variables. The next choice I could have is 2 negative helicity particles and 1 positive helicity particle. And here, the overall constant might be different. So let me put a different normalization here. And referring back to the formula, if you plug it in here with negative, negative, positive, you'll see that you get 1, 2 cubed over 1, 3, 2, 3. Then the next choices are yeah, okay. Yeah, actually, those are the only 2 choices, but I cheated a little bit because, yeah, I misspoke a little bit. For H1 plus H2 plus H3 greater than or equal to 0, you can have the other type of amplitude. That is the one that depends on square brackets rather than angle brackets. So I forgot to write it, but it's basically the same thing. It's basically the same formula, except you change the sign of everybody in the powers. There's a constant again. Oops. Yeah. And 1, 3, H1 plus H3 minus H2. Okay, so to finish my little chart, I'm sorry. I was trying to make a complete chart of all 4 possibilities, and then I realized that I forgot this. So now I can finish my chart. If we have 1 minus 2 plus 3 plus, we can have yet another arbitrary constant times 2, 3 to the power 3 over 3, 1, 1, 2. And if we have 1 plus 2 plus 3 plus, we can have yet another constant times 1, 2, 2, 3, 3, 1. Okay. Okay, so now we're completely done. There are only 4 different types. 1, 2, 3, 4. There are only 4 different types of massless 3-particle amplitudes that have in 4 dimensions that have a well-defined limit in the Minkowski space limit. When you analytically continue back to Minkowski space, real momenta in Minkowski space, and these are all non-perturbatively exact. and there are only 4 possible undetermined constants here. Okay, we'll say a little bit more about, let's see, actually I should say, no, I'll say that later. Okay, there's something really remarkable here. Let's stare, for example, note that the right-hand side, well, let me just write, each formula, each amplitude is fully, I don't want to write each amplitude. I want to write each formula is fully antisymmetric under the exchange of any 2 particle labels. Okay, like let's just stare at this one here. Okay, stare at this last one here. Okay, yellow is really hard to read. Stare at this one here. If I exchange particles 1 and 2, then I get a minus sign from this factor, because remember that the bracket is anti-symmetric under exchanging the particle labels. This switches into 1, 3, and this switches into 3, 2. But if I want to put them back into the order where they came, I get a minus sign from turning that 3, 2 into 2, 3, and I get a minus sign from turning that 1, 3 into 3, 1. So overall, I get 3 minus signs. So this thing is anti-symmetric under switching particles 1 and 2. And you can easily check that all 4 of these formulas are anti-symmetric under switching any pair of particles. However, spin 1 particles must be bosons, so their amplitudes must be symmetric. Must be fully symmetric under exchange of any pair. So it seems that we've arrived at a contradiction, and the only way to resolve this contradiction, the resolution, is that alpha equals beta equals gamma equals delta is 0. Right? The only thing that's both symmetric and anti-symmetric under exchange of 2 labels is the quantity 0. So what we've learned, what we've concluded, is that a massless spin 1 particle, i.e. something like a photon, cannot have a self-interaction. Okay. Now, if you've studied Lagrangians for spin 1 particles, you know that this is true. And it's true because it's impossible to build a gauge invariant term in a Lagrangian that would introduce such an interaction on shell. Now, we've arrived at that conclusion without any need for us to consider gauge invariants or Lagrangians or fields, just by looking at the properties of the amplitudes themselves. Now, it would be pretty disappointing if I went through all this song and dance and introduced all these concepts only to find that 0 is the only solution. Fortunately, So you probably already know the way around this. Well, let me just say, to get interesting non-zero amplitudes, we allow there to be, let's say, n different species of particles. And so what we'll do, for example, is, let me not rewrite all of the formulas. Okay, here I've just rewritten one out of the four, but the same thing, you imagine the same thing for all of them. So here, A, B, and C label which of the n types you are scattering. Okay, so instead of considering a single type of massless particle, we consider n different types, and here's a scattering amplitude. The coefficient here can depend on the types of particles you're scattering, but we require that beta A, sorry, not alpha, ABC must be antisymmetric under exchange of any pair. Okay, and when we do this, then we get two minus signs. Let's say you exchange particles 1 and 2. We've already discussed that you get a minus sign from this factor, but you also have to exchange the A and the B. So when you do that, you get a minus sign from this factor, and overall you'll get a plus sign as required. So you can have consistent, non-zero interactions between collections of massless spin 1 particles, as long as they have this type of antisymmetric coupling constant.
May I interrupt?
Absolutely.
Yeah, so maybe this is something I missed, but if I did a switch between 1 and 3, doesn't the numerator and denominator get, I mean, aren't they inverted? So how do I see that it's antisymmetric?
Ah, yeah, okay, thank you, I'm sorry, yes. Yeah, I was very unclear about that. Yeah, so, whoa, yeah, so strictly speaking, okay, good, yeah. So in the example I did here, this is the example I looked at in detail. Okay, here in this example, I'm honestly allowed to switch all 3 particles because they all have positive helicity, right? 1, 2, and 3 all have positive helicity. In this example, and thank you for catching me on this because I was, yeah. In this particular example, you should only, strictly, you can only allow yourselves to look at what happens if you switch particles 2 and 3, because they have, you should look at a different formula. Let me be a little bit more precise about this. Let's do this a little bit more. Earlier, I wrote this formula. Now, if you want to contemplate what happens if you, let's say you want to contemplate what happens if you switch particles 2 and 3, okay? Then you're going to end up needing to know the formula that I haven't written, okay? You're going to need to know this formula that I haven't written yet, right? Minus plus minus is not in the list of 4 things that I've written so far But you can refer back to this original formula here to figure out what it must be. Okay, and if I don't make a mistake, I'm sorry, this is illegible, this is a 3. Okay, if I don't make a mistake, this should be 1, 3 cubed. Okay. Some people use a slightly different convention, but this should be now 1, 2, 2, 3. Okay, so now the question should be, if we start with this formula and exchange 2 and 3, do we arrive at this formula or do we arrive at minus this formula? Okay, and you see that you arrive at minus this formula because of the following reason. When we exchange 2 and 3, this factor goes to this factor goes to this factor, but this last factor picks up a minus sign. Okay, so thank you for catching me on that. My earlier argument was a little bit too quick about the minus signs. You do have to refer back to this original formula and write down all possible permutations with all different particles having plus or minus. Does that fully answer your question?
Yes. Thanks a lot. I have an additional question. I mean, maybe it's quite tangential, but when you complexify the momenta, is there any point in thinking geometrically what is happening? I mean, in terms of in actual Minkowski space.
Yeah, there's a lot of beautiful geometry there, and I think I'll get to it in my next lecture.
Okay, thanks.
I'll defer on that question. Okay, now, good.
Hello?
Was there another question?
Yes. Can you hear me?
Yes.
In the same formula, 1 minus 2 minus 3 minus, suppose if you were to exchange 1 and 2, you would still get a minus sign, right?
Yes.
And that would sufficient to tell us that beta should be 0 because of the...
That's right. Yes, that's correct. That's enough for that argument. But I was looking ahead to requiring that this thing should be fully antisymmetric, even under like B and C. But anyway, but yeah, thank you. You're absolutely right. For the purpose of showing that there's no self-interaction for a single particle. That's right. Thank you. Okay, good. All right. Let's look. I have enough time to look at some 4-point amplitudes. Now here, for the first time, I will have to introduce perturbation theory. And the reason is the following. So as I emphasized a moment ago, the 3 particle amplitudes that we derived are valid non-perturbatively. Now, what I'm going to do in the next few minutes is make an argument that appeals to unitarity in order to constrain some 4-point amplitudes that I want to write down. Now, we know what the constraint of unitarity looks like at tree level. So let me, tree level unitarity looks like the following. What I mean by that sentence is, if you ask the question, what is the mathematical constraint that is required in order for you to say that such and such an amplitude satisfies unitarity at tree level? And the mathematical constraint is what we usually call factorization. it says that if you have some amplitude and you dial the kinematics so that you approach close to where some intermediate particle is going on shell. So let me write here, take a limit where some intermediate P is going on shell. That means P squared equals 0. Still discussing Massless cases. Then this amplitude should behave like in other words, I don't think I've said this very clearly, I'm sorry. So what I mean is that amplitudes, tree-level amplitudes, have simple poles, and the locations of those poles are precisely in those places in Mandelstam variables where the form momentum of some intermediate particle is going on shell. And if you imagine, using Feynman diagrams, so here you have some, in this particular example, I've drawn 8 external particles. Such an amplitude will have many different poles. And if you ask, what is the residue? If you look at all the Feynman diagrams where the process splits into 2 pieces connected by a single propagator carrying P, then these Feynman diagrams will be the ones that contribute to the residue of this amplitude near P squared goes to 0. And the actual residue at that pole will be the product of the left amplitude on the left and the amplitude on the right. Okay, so I'm appealing to this mathematical statement of tree-level unitarity only because nobody really knows precisely what is the analogous crisp mathematical statement that encapsulates the requirement of unitarity non-perturbatively. Okay, so there's a whole field of theoretical physics called the conformal bootstrap, which is built around imposing the requirement of unitarity for conformal field theories, where things are much better understood in that respect. But our understanding of the mathematical requirement of unitarity for general quantum field theories, ones with S matrices, we're not quite at that stage yet. But in order to make some interesting statements for the rest of today's lecture, I will make this assumption, and that is, I'm just highlighting that this is the first time I'm resorting to perturbation theory. Oh yeah, and in this example, both AL and AR are tree-level amplitudes.
May I ask a question?
Absolutely.
Yeah. So does this argument of unitarity also follow from the usual optical theorem?
Yes, this is exactly the implication of the optical theorem. Yes, that's right.
Okay, so I mean, is there a way to see that? Because in the usual optical theory, we have this T dagger T is equal to this imaginary part of that amplitude.
Yes, yeah. Yeah, that goes a little bit beyond the scope of my lectures. Yeah, I should say, I mean, certainly unitarity does imply constraints on amplitudes at loop level. That certainly is the case, and certainly it is the case that you can look at cuts or discontinuities of loop level amplitudes and relate them to products of lower loop amplitudes. In such cases, A left or A right might not be tree level, but could be higher loop amplitudes themselves. That is all certainly true, but just for the purpose of what I'm going to be doing in the next section, I'm only going to be using tree level unitarity. But indeed, this is exactly this formula is exactly an encapsulation of the, let's say, the tree level constraint of the optical theorem. You know, what would the analog of the optical theorem at tree level? Okay, but anyway, so the immediate application that I want to use is to look at a 4-particle amplitude. Now, there are many different amplitudes you could look at. We've already admitted that we need to allow ourselves to have n different species of particles. So let me just take a look at this one. Now, you can pull out a factor here. This factor that I've written here has the correct weight. It's already been an hour since we've discussed the weight, so let's review this formula and see that it works. Particle 1 has negative helicity. So if we rescale particle 1 like this, then the amplitude should rescale by a factor of t to the -2. That's what it meant for particle 1 to have negative helicity, -1. And if we look at this formula here, we see that the only place where particle 1 appears is right here. And so indeed, that bracket, the angle bracket, involves the lambda variable here. So that will rescale with a factor of 1/t squared, so that works. Particle 2 is the same. If we look at particle 3, if we imagine rescaling particle 3, the fact that particle 3 has positive helicity means that this should rescale by a factor of t to the +2. And we see that that works out because the only place where particle 3 appears is right here. It scales by a factor of t to the +1 power, and it gets squared. So let me put a check mark here. Okay, and particles 2 and 4 work analogously. This factor takes care of the spinor weight, but we could have an arbitrary function here of the Mandelstam invariance, st and u, where s is p1 plus p2 squared, t is p2 plus p3 squared, and u is p1 plus p3 squared. There's a question in the chat about the conformal bootstrap. To a large extent, the philosophy behind the conformal bootstrap and sort of the amplitudes program is very, the philosophy is essentially the same. It's just the tools we have at our disposal, it's a slightly different set of tools we have at our disposal. So I won't say more about that. Throughout my talk, I've occasionally made vague references to how this sort of such and such a thing resembles such and such a thing in conformal field theory. So there's a lot of overlap in the philosophy, but the tools are quite different. Because the questions we're asking are quite different. They're looking at primarily at endpoint functions of local operators, whereas we're looking at scattering amplitudes. Okay. So we have this arbitrary function here that can't be determined by the considerations of the spinor weight alone. Now, dimensional analysis, which I haven't mentioned before, but this is an important constraint as well, tells us that an n-particle amplitude must have dimension energy to the power 4 minus n. And the way to see this is you want to imagine taking your amplitude, squaring it, and then integrating over an n-particle phase space to get a cross-section. And there are various other factors that appear if you look up in quantum field theory book, the formula that relates differential cross-section to the square of a scattering amplitude integrated, there's some flux factors and other things. If you put that all together, I mean, this is a fun exercise. If you haven't done it already, try to prove to yourself that an n particle amplitude should have dimension of energy to the 4 minus n power. Now the brackets, these things each have power of energy, or have dimension of energy. So if we look back at our formula here, where this f is undetermined, our undetermined f should have dimension uh, 1 over energy squared. Okay, so simple ansatz with only simple poles T times U. Here I've got 3 undetermined coefficients. So this thing that I've written down at least has the correct dimensions. Now, of course, there could be other terms. For example, there could be polynomial terms. But as I've made clear, I'm going to invoke an argument that, that applies tree-level unitarity. So that involves looking at the residues of poles of this thing. So the argument that I'm going to use in a moment is not going to be sensitive to any polynomial terms. And on the other hand, from our knowledge of the way Feynman diagrams work, we shouldn't expect anything with higher order poles either. That would immediately violate factorization. There's also a question in the chat about whether little group can be extended to massive particles. Indeed, I wanted to say a word about that. I won't be able to do so today for lack of time, but I'm almost done with where I wanted to get for today. Okay, so let's look at the pole.
Sorry, isn't F 1 over energy power 4, or maybe I'm missing something?
Oh, I'm sorry, could you repeat your question, please?
Isn't F 1 over energy power 4? Am I missing something?
Okay, let's make sure I probably screwed up something. Oh, yes, I've screwed up something. Thank you. Yes, because here we have a 4-particle amplitude, so it should be dimension. Oh, thank you, yeah. What have I screwed up? I have a 4-particle amplitude, so it should be dimensionless. Then I've got, yeah, thank you. I have screwed up something.
I mean, S and T have dimension of energy square, right?
Thank you, yes, thank you. Yeah, thank you. Okay, yes, right. So the only typo is here. This should be 1 over energy to the 4. Yeah, 4-particle amplitude should be dimensionless. Here, I've got 4 powers of energy sitting outside in my prefactor, so F should have dimensions of 1 over energy to the 4, and indeed it does, because all of the ST and U are energy squared. Thank you. Okay, let's look at the pole where P1 plus P2 squared is going to 0. Okay, so we're taking S to 0. The residue of that pole, the residue at that pole is limit this is S, right? So we want to look at the residue of the pole when S goes to 0. We get this prefactor. Okay, and now there are two contributions. So we get this piece has a pole as S goes to 0, and that gives the contribution here. I've pulled out a 1 over T. This thing also has a contribution. Recall that S plus T plus U is equal to 0. So when S is 0, U equals minus T. So this thing gives a contribution that's minus C times US, because I pulled the T out front. I turned this U into negative T and pulled it out front. So sorry if that was a little too quick, but there are two contributions to the 1 over S pole. The first term has a 1 over S pole with this residue, where I pulled a T out front, and the third term has this residue where I've turned the U into negative T and pulled it out front. Okay, now by factorization, this must equal a product of 3 particle amplitudes summed over intermediate states. So if I imagine drawing a schematic diagram like this, let's say that I'm exchanging particle type E here. Okay. What I've learned, okay, if you plug in the actual amplitudes so above, earlier in the lecture, we discussed what these 3 particle amplitudes are. And if you plug in those formulas, here we've got the residue of the pole. You find that CST minus CUS has to be the sum on E of what I was earlier calling beta ABE, beta CDE. Okay, now I'm almost done. So this is a constraint between the coefficients beta that appear in the 3 particle amplitudes here and here, and the coefficients C that appear in the 4 particle amplitude. I got this constraint by looking at the S pole. You could also look at the T pole and the U pole, and you get analogous constraints. They look like this. BCE, beta ADE, and CUS minus CTU is sum on E, beta CAE, BDC, BDE. Now let's look at the 3 equations here on the left. Okay, these 3 equations add up to 0 because that cancels that cancels that, and that cancels that. So therefore, a solution to this set of constraints only exists if the right-hand sides also add up to 0. Oops, I wrote that in the wrong order. And this is the Jacobi identity. So we've learned that the consistency requirement of tree-level unitarity is enough to demand that the 3-point self-coupling of a massless spin 1 particle must be the structure coefficients of a Lie algebra. Okay, and I'll end my lecture. I'll take questions, of course. I'll end it here for today, although there were a number of interesting questions that have been raised that I will further discuss in the following lecture. But I see already there's something in the chat, so let me. Yes, excellent. So there's a question in the chat about these formulas. So there were 4 fundamental formulas that I wrote. These 2. So 1, 2, 3, 4, and of course various permutations of them. And the question in the chat is, do these take into account possible interaction terms from higher dimension operators? And indeed, one way to interpret what we've done here is that we've classified all possible higher derivative operators that can have an effect on 3-point amplitudes. Let me be a little bit more precise about that. Interactions of type 1 minus 2 minus 3 plus and 1 minus 2 plus 3 plus are the only 2 you get from pure Yang-Mills theory. So if you write the usual Lagrangian for Yang-Mills theory, something like this, okay, you'll get the 2 interactions of these types that I've written above. So you can see that already from dimensional analysis. In pure Yang-Mills theory in 4 dimensions, you only have a single coupling constant here that's dimensionless. Now, if we refer back to these formulas, okay, let's look at these 2. I said that an n particle amplitude should have dimensions of energy to the power 4 minus n. So for a 3 particle amplitude, our amplitude should have dimension of energy to the 1st power. Now take a look at this one here. This factor here has dimension of energy to the power 1 because there's 3 powers in the numerator and 2 in the denominator. So that means this coefficient should be dimensionless. And that would be consistent for it being the coupling constant of a non-abelian gauge theory. But if we had an interaction of this type, then this coupling constant must have dimension energy to the power -2. That's the only way to ensure that overall this thing has the required dimension of energy. So that can't come from a pure Yang-Mills interaction. Instead, that comes from a trace F³ interaction. The two a 1 plus 2 plus 3 plus and a 1 minus 2 minus 3 minus come from interactions of type trace F³ with a coefficient that has a dimension of energy to the power -2. And now you see, I mean, normally when you're trying to classify higher dimensional operators at the level of Lagrangians, there's a lot of work to do. Okay, in this particular example, it's quite minimal work, but you have to worry about, you have to worry about the fact that under field redefinitions, your amplitudes don't change, and under adding total derivatives or integrating by parts in your Lagrangian, your scattering amplitudes don't change. So if you're trying to classify, I mean, this has been done in the literature, but in general, it's a hard problem to classify the truly independent set of operators, set of higher dimensional operators that are relevant to any particular n-particle scattering process. But here, I mean, this was a particularly trivial example. It does get harder in more general cases, but in this trivial example, sort of the classification came out for free. It was essentially trivial. We saw there were two different types of interactions and their parity conjugates. 3 and 4 are the parity conjugates of 1 and 2. And one of them corresponds to a Yang-Mills interaction and the other corresponds to an F³ interaction. And that's all you can have. Anything else, any other operator would either vanish on shell or be equivalent to one of these under a field redefinition. So I think that hopefully answers the question in the chat. And I'm definitely, okay. Does the factorization of the 4-point function occur non-perturbatively in CFTs? Yeah, there is an analog of the operator product expansion. When you're talking about CFTs, the operator product expansion is the analog of what we're calling factorization here. I mean, again, it's only an analog. It's not exactly the same thing, but the conformal bootstrap is built around, well, I'm not an expert on the conformal bootstrap, so I shouldn't be speaking for it, but it's the closest analog to what we do here with factorization. And it's non-perturbative. I'm definitely available for other questions, but that's the end of where I wanted to get.
So, for the 3-point amplitude, you said we should analytically continue onto the Minkowski locus, and that should make it smooth, right? But there should be poles for external movement.
Oh, good. Yeah, thank you. Yeah, so of course, amplitudes do have poles. I mean, we use the fact that I looked at the pole of a 4-particle amplitude. But my argument with when I was talking about the 3-point amplitudes, there was a more serious problem. Usually, you want your amplitudes to be well-defined for generic momenta, and then have isolated poles for certain momenta. Like the 4-particle amplitude is perfectly fine for generic amplitudes, but it has a pole when S goes to 0. It also has a pole when T goes to 0 and a pole when U goes to 0. The problem with the 3-point amplitude that I looked at here was more severe. Here, we were not worried about a pole that exists for certain momenta. Here, it's just the entire amplitude was just infinite, period, as soon as you hit 3-particle kinematics in Minkowski space. So it's a little bit of a different flavor. And here it was a more serious problem.
Okay.
I have a question. So earlier we had some discussion about betas being completely antisymmetric or not, these coefficients, right? And only if like all the helicities were same, they were completely antisymmetric.
Yes.
Right? So now when we did this factorization and we got the Jacobi identity, we inferred that these are structure constants of some Lie algebra.
Yes.
So now if it's a compact Lie group, then there is a basis in which the structure constants would be completely antisymmetric.
Yes.
Right. So what is the statement about this? Do only these betas appear which are completely antisymmetric, or?
Yes. There may have been some temporary confusion on that point due to for which I apologize. The confusion was resolved by realizing that you don't need that as soon as you have, let's say, let me look at this formula. Now, as soon as you have this formula here, then that tells you, then just by replacing particle, let's say replacing, so that tells you, I'm sorry, I'm not speaking very clearly. We actually have to go back to this. The point is that it should be the same. Where did I do that little calculation? Here we go. Yeah, right. This little calculation. When I did this calculation, it should be the same beta that appears here.
Okay, I see. Yeah.
And if I put A, B, C here, yeah, it should be the same beta. Yeah.
Yeah. Okay. Thanks. Yeah.
Yuten, there were some people with their hands raised. Do you want to call on them, or should I?
Oh yeah, sorry, I didn't see the hands. How do I unmute them? Do I just press?
Well, some people might have. If you've raised your hand, but your question has already been answered, you can lower your hand. But there's still one raised hand by.
Unmute. Okay.
Maybe it's me. Can I ask a question?
Yeah. Sure, go ahead.
So for these 3-point amplitudes with all of them are spin 1, they are going to be 0, right? When you restrict to the real momentas?
Yes.
Okay.
Yeah. So strictly speaking, exactly. So it's amazing how much information you can get out of something that's 0. But but there's 0 for strictly real momenta. But it's useful to know that they're non-zero for complexified momenta, because that gives you a lot of analytic information about more general amplitudes.
So I guess I don't see any more raised hands. Okay, so so thanks, Mark. Yeah, you must be exhausted. Okay, so let's give a round of applause for Mark.